Paired sample. Okay, so now here we got two groups. Let me blow this up a bit so we can see it. Here we have two groups. Actually, we don't have two groups. We have 8 subjects. These are our 8 subjects. Each one of these lines represent a subject. We weighed the subject before putting him on a high fiber diet, and we weighed him after putting him on a high fiber diet. And we did that for each of these 8 subjects. So this is not two different groups. It's not independent samples. It's not one group of people, and then we put a second group of people on high fiber diets and then weighed them. It's the same group of people. So we're looking at this from the perspective of, was there a difference here? Okay, well, let's measure actually that. So we're going to compare the mean of before to the mean of after. Well, that would make it 2 independent samples. There's a much more efficient way to do that. And that is that since each value represents an individual's weight before and after this intervention, we're just going to calculate the difference between these weights. Okay, so I'm going to calculate the difference before and after. It's 162 minus 168. Okay, this guy ate a lot of bran flakes because he put on weight. Okay, and I'm going to copy that down. And there we go. And we say a couple of people gained weight, a couple of people the weight before was greater than the weight but this actually, tell you what, just to make it more understandable, I'm going to do this a little bit different. I'm going to say it's equal to the weight after divided by the weight, minus the weight before. Okay, and I'm going to copy that down. Okay, we're going to get a lot of negative numbers, but it might be a little bit more intuitive. This person lost 37 pounds, this person lost 15, so on and so forth. Now, instead of finding the average weight before and the average weight after, I'm going to find the average difference. And I'm going to take the average difference. The average difference is, on average, these people each lost 12 pounds. Okay, so now, instead of dealing with trying to figure out whether the mean before and the mean after is different, I'm going to look at the difference. What would we expect the difference to be if what would we expect the difference to be if there was no benefit to eating fiber, a high fiber diet to lose weight? What would I expect this difference to have become if it had nothing exactly right? Our expectation is that should have been 0. So instead of comparing the means of before and the means to after, we're going to compare the mean difference to the value 0. So we're going to take this 2 sample t-test and turn it into a more efficient version of this, a single sample t-test. Okay, so the next thing I got to know for this is my standard error. So this is my mean loss. Okay, my standard error for my standard deviation for my mean loss is going to be equal to standard STDEV parentheses. Okay, there we go with that. And it's 14 pounds, and my sample size was equal to 8, right? So if the sample size is 8, what are we dealing with here? Are we dealing with the Z distribution or the T distribution? Dealing with the T distribution because it's small. Okay, so my sample size is 8, so my standard error is going to be equal to, the standard deviation of my sample divided by the square root of my sample size. And that's equal to 5.044. So now my null hypothesis, I'm going to use a 2-sided null hypothesis. Now you could argue that, well, the only reason we'd be doing this is if we thought it was going to drop the weight, make people drop weight. But in fact, some people gained weight. So my null hypothesis, since I want to do a rigorous test, I don't want to take any shortcuts, and I had no evidence going in how a high fiber diet would affect people. So I am going to make my null hypothesis. Let me get a new page here. Okay, I'm going to make my null hypothesis. My null hypothesis is that the mean weight before is equal to the mean weight after, and my alternative hypothesis is the mean weight before is different than the mean weight after. Another way of my phrasing this is going to be my null hypothesis is that the mean difference is equal to 0, and my alternative hypothesis is the mean difference in weight is not equal to 0. Okay, this is going to be a more rigorous test because we're going to have to compare it to the z-score of 1. Well, a t-score of whatever it is for a 95% confidence interval of 0.05 with double tail 2.5% on one tail, 2.5% a bigger t-value, right, than we would have if it was going to be a one-sided test. Okay, so now I'm going to go ahead and do this calculation. I'm going to do it over here. Okay, so what is it going to be equal to? This is going to be equal to, it's going to be equal to the mean weight loss, x bar, minus the number I'm comparing it to, which is 0. Right? I'm comparing it to 0. I want to prove that it's different than 0. Divided by this, that's how far apart they are. Now I'm going to divide by the standard error so I know how many t-scores or z-scores apart they are. In this case, t-scores. And they're 2.35 t-scores apart. Well, now I have to go to find out if that t-value, if the value of t I just calculated, does this t, is it bigger than t critical? And if it's bigger than t critical, I can reject the null hypothesis. Okay, so I'm going to go to my t-table again. Whoops, t-table. P-table, okay. So now what do I have to look up here? It's 8 degrees, it's 8, sample size of 8. So we're dealing with two-sided, so it's 95%. T is 2.5% on each tail. So this time, though, my degrees of freedom is 7. My critical value for T is 2.365. Okay, my critical value for T is 2.365. Okay, which is, let's see, 2.365. Can I reject my null hypothesis? That's my critical value. Can I reject my null hypothesis? No, I can't reject my null hypothesis because this such a small sample size that I needed to be, in order to be sure, not with a 5% chance of being wrong, that they're far enough apart to say that they're different, that's really different than 0. This I had to exceed my critical value of t from that table for that sample size with that degree of freedom. I had to exceed 2.365. As it turns out, it's only my t-score, my distance apart in standard errors is only 2.35. They're not far apart enough for me to reject the null hypothesis. Okay, so I'm going to do one more example, which is independent samples t-test. Now, you might remember we did one in class, and we mimicked one that Professor Waldron had done during the lecture video. And we got a big value. I think we got a t of 10 or something like that. As it turns out, we forgot to take the square root of the value that we found, the fractional value that we found. We forgot to take the square root of it. So it would have been a smaller number. It would have been like 3.6 or something like that, which would have been the right answer. But we made in that lecture, in that lab session, made a little bit of an error in our haste. But in either case, we rejected null hypothesis because the value with 3 point something 3.5 or whatever it was still big enough to exceed the critical value of t that we needed. So now the only problem is that was pretty tedious calculation, if you recall. We had to calculate we had to calculate the standard deviation from the sample involving the sample sizes of each group and so on and so forth. It was rather difficult to do. Well, SPSS comes to the rescue in this. I know some of you don't think it's coming to the rescue, but trust me, it comes to the rescue in this case. I'm going to open up an example where we're going to do this calculation using independent samples t-test using SPSS. And I'm going to open this hourly wage data.sav. Okay, when SPSS opens up, we're going to take a look at the values, the variables that we're working with.
It's 10 o'clock.
When you're doing this, you can in this case where we're looking at a two-sided test, we can ignore the value of the sign. We just need them to be that far apart. Okay, so I'm going to look over here, and I'm going to say, what do we have here? Well, we have a bunch of people that are hospital workers, some of them who are clerical workers, some of them who are other staff type workers, hospital. They're identified as hospital and an office. If I go to the variable view, I can look at that that variable position, and I can click in here to the values, and it'll tell me 0 represents hospital personnel, 1 represents office personnel. Okay, that might be like highly paid people, like public health professionals or administrators, public health administrators like you guys, right? Hopefully they'll be the highly paid group. So at any rate, if I go back to the data view, I know that that's really a 0 and 1 back there. I can flip it on and off there so you can actually see that. The data view, values on, values off. Okay, and here is the hourly wage for each of these groups. For each person, right? That's a person, that's a person, that's a person, and so on and so forth. And there's a lot of them, right? We had to do this, we had to do the math on this, we'd be here for quite a while. So we're going to use SPSS to do this for us. So as always, when we're using SPSS to do for the kind of work that we're doing, we almost always go up to analyze, and we choose the information that we want. If I just want descriptive statistics, I could go into descriptive statistics and explore like we did for the last test for exam 1. And I could say, let's take a look at the hourly salaries, but break it up by nurse type, by the position. Okay, put that into the factors list. And okay, give me the descriptive statistics. Okay, and it'll break it up for us. And it turns out that hospital nurses, office nurses, or hospital nurses, well, hospital nurses seem to make a higher average hourly salary than office nurses, whatever this is supposed to mean. And here's the 95% confidence interval, here's the standard error, and so on and so forth. Well, this is nice. This gives us an idea of the kind of data that we're dealing with. Here's the box plots and stuff like that. Now we want to see if we have enough data. This is a very large sample size, so it's conceivable we might. Since we know just by looking at the descriptive statistics that in our samples, in our 2 samples, hospital nurses and office nurses, we know that the average salary in our sample for hospital nurses, they have a higher average salary than office nurses. So now we want to know, can we say with 95% certainty, 5% chance of being wrong, or less than 5% chance of being wrong, that we can say with that level of certainty, that chance, less than that level chance of being wrong, can we say that the true mean salary for all hospital nursing personnel and office nursing personnel are different? Okay, so I'm going to do a 2-sided hypothesis. So, and in fact, SPSS virtually always does 2-sided hypotheses. Now, in order to do that, right, to get my descriptive statistics, which I could have used or not used, I could have just gone directly to comparing the means for these 2 groups. Instead of going to descriptive statistics and frequencies or explore or descriptives, I'm going to go to compare means. Well, we've already seen how to do a 1-sample t-test. We've already seen how to do a 2-sample, a paired sample t-test. Well, the one that's left here is independent samples t-test. That's what we have here. Two groups, two independent groups. Some of the people are office nurses. Some of the people are hospital nurses. So I want to compare means, independent samples t-tests. Okay, so I'm going to test variables. I'm going to put in the hourly salary is what I want to compare. The means for hourly salary is what I want to compare. And the grouping variable, I want to group it by position type. Or and notice it asks me to actually define the two groups. That means it wants you to tell it that the group is that one group is zero, has a one represent a zero represented and a one represented. Okay, it does that because if you had a variable for position, right? You could have had another position like hospital nurses, office nurses, visiting nurses, ER nurses. You could have many variables in there, and the t-test only do compare two means at a time. So if you wanted to compare hospital nurses versus visiting nurses, you might have said, well, compare 0 to 3 if that's what represented that that kind of position. Okay, so now I'm going to click OK, and it's going to calculate a t-score. Now, you guys might remember that one of the issues when we calculated a t-score for independent samples, we had two different groups, two different samples. So the variability of one sample could be different than the various. So there's not just one standard deviation that we're dealing with. Well, if the standard deviations are the same, we might, or very close to one another, we might be interested in combining the two of them into a single standard deviation that we can calculate our standard error from. If the standard deviations are dramatically different, we may not want to do that. These calculations for standard error and for degrees of freedom can get relatively complicated depending on whether you make these assumptions. SPSS will do this for you. Okay, and the way it does it is that it says, okay, let's compare the hourly salary, the average hour salaries for hospital. It's $20.67 per hour. Office is 18.66. Standard deviation, standard error. If you look at them individually, looks like they're a little bit different, but I don't know, maybe not. They look pretty much different, don't they? This one's 50% more than this one is. Let's see what we should do with this. SPSS does a test called Levine's test for the equality of variances. It does a test. This is not part of the t-test. This box, this 2x4 box right here, is a separate test. And what it does is it first assumes, just like a null hypothesis, it assumes that the variances are equal. Okay, that's our null hypothesis. Then it does a calculation to test that. It calculates an F-score and a significance. This is a probability. This is a probability of being wrong if we reject this null hypothesis. Well, in this case, the probability of being wrong, significance is the same thing as probability of being wrong for SPSS, p-value in other words. The probability of being wrong is less than 5%, then we ignore the top line and we use the bottom line instead, which is calculated based on the variances not being equal, not assuming equal variances. Okay, so we're going to use the bottom line. The bottom line, we determined that the t-test, the difference between the two means over the standard error, is 11.879. That's a pretty big number, right? Okay, and the probability of being wrong if we reject the null hypothesis is very, very low. It's less than 0.1%. We need this value, two-tailed significance, p-value, two-tailed. We need that to be less than 5% to reject the null hypothesis. Now, it doesn't matter if I put in the 1 or the 0 first. So this is less than 5. This is a big t-score, and the probability, SPSS, instead of using just a critical value for t, right, it has all the t values for everything built into it. So it actually can calculate a p-value, a probability of being wrong, just the same way as you can do a z probability. You can calculate p for a z score by going to your tables SPSS can do it for a T-score as well. Okay, and it determined that less than 0.1% chance being wrong if we reject the null hypothesis. So we reject the null hypothesis that the mean hourly salary for hospital nurses is equal to mean hospital salary for office nurses, and we accept the alternative that they're different. And we can see that, as it turns out, that hospital workers get paid more than